into account, but we know that the value of G depends on the height, the distance to the center of the Earth. So if you really have a huge variation in Y, the value of G will change, so the magnitude of W will change. And here you can see also that it is not a straight path. So you would have to use a formula like this to figure it out. Luckily, when we look at the weight, we're going to see that we can compute this in a much easier way using potential energy. So that's work. And why do we talk about work? What is the theorem from physics that involves work?
Law of conservation of energy.
It's almost that, yeah. It's not exactly that, but it's almost, yeah. I mean, it is a law of conservation. It's because energy is not necessarily conserved, and the theorem is still okay.
Well, you know that the energy is, if it's not conserved, the energy is going to be the energy initially plus any work added to the object at the time.
Yeah.
So it'd be Ki plus, or it'd be Ki plus.
What is K?
Oh, K is one half mv.
So the kinetic energy.
And then plus the integral of the force over the distance equals the Kf plus Uf.
What is the opposite of change in energy?
You're adding too many terms in your equation, but it's pretty good. So the reason why we talk about work, it's because we have the work energy theorem. And actually energy in there means kinetic energy. And what does it say? It says that the change in kinetic energy, so this is kinetic energy, that's the notation of the book. So between some final instant and some initial instant, it's equal to the net work done on the object. So what is the net work? It is the work done by the net force.
U?
Yeah, I'm getting confused as well. So the net force. Or you can say also that it is the sum of the works done by all of the forces. So kinetic energy, we know that T is defined as 1/2 m this way. So before doing some examples, let's look at some common values of work. So the work done by a spring, the work done by gravity. If you go from some y initial to some y final, one object, and you do this. So of course, it says the object has mass m, so it has some weight, w, which is of course mg. What is the work done by w when we go from I to f? So it's not the net work, because of course the object would not go up just because of W. Well, if you wanted to use that, but here I'm just talking about the general formulas to compute the work. How do you find the work done by a weight? It's mg times what?
H. Or delta H, sorry.
Right, yeah. So it's going to be mg times the change in height. Is it yi minus yf or yf minus yi?
YF minus YI.
If I do yf minus yi, what is the sign of the work in that case?
Positive.
Positive.
Does W do positive work or negative work here?
Positive.
Here, it's W is basically opposite to the displacement. I mean, not always exactly.
Oh, yeah, sorry.
So it's going to be negative, right? So then, it's not what you have here. Here, the work done by the weight is going to be y initial minus y final. Or you can put a minus sign, and you say minus mg y final minus y initial. Of course, taking the y-axis, that is going up. If your y-axis is going down, you have to flip the signs here. What about the work done by a spring?
1/2 k delta x squared.
Okay, so let's say I have a spring. So we have it at some position I here, and then it goes to some other position. F over there. And so we have some displacement from I to F. So there is a force acting on the object by the spring. What is the value of the force by a spring on an object? How do you find it?
It's the coefficient.
K is 10.
Okay, so remember that we have F is equal in magnitude to K delta X, so some X minus X naught. What is X naught?
Its position.
The neutral position of the spring.
Right, so, well, if you want precisely, it is the rest position of the spring. That is when it is not stretched or compressed. So to find the work done by F, when we go from an initial position to a final position, it's also quite easy. That's what you said, Josh. So it's going to be 1/2 K. So K is called well, the spring constant. Sometimes you can call it, this is called Hooke's law, but this is called spring constant. So it's going to be a difference between x squares. Is it x final or x initial or?
You want if f is bigger than I, you want the work to be negative.
So
The work happens in two different directions on the way down, if it's reverberating. So
well, let's say, so we have to hold this.
The displacement of the force in opposite directions, essentially, right?
So if you pull on the spring like this, let's say the spring is stretched initially, and I pull more on it. Is the force doing positive work or negative work?
negative work.
Negative work. So this formula should work in that case.